Thank you. So yes, I'm Sebastian. It's my colleague Peter. We're kind of sharing this talk. So Peter will take over later. So yeah, this talk is on streamlining performance analysis workflows using compiler technology and trying to get instrumented code that serves your purpose, your measurement purpose. So we had quite a few talks that involved SCORP, and one of the things SCORP does is do code instrumentation to enable the collection of non-statistical fine-grained performance data. And this is something that's also used by, for example, Tau. The difficulty here is that the full code instrumentation can lead to very large overheads if you're not careful. And this can reach orders of magnitude for fully instrumented codes, which may skew the performance results. To kind of illustrate this, on the right, I have some measurements from my work here, where we did some open form benchmarking, and you can see that the first two are GCC and Clang measurements, and then on the right there's the initial SCORP measurement using full instrumentation, and that's about 2 times slower, even with the pre-filtering that SCORP does. So overhead management is really key and can be done via selective instrumentation. For example, there's a SCORP score tool when you're in a SCORP environment. However, for the user, this kind of results in what we call the build, run, analyze cycle, which is where the analyst first builds the application and instruments it, then runs and profiles it, and then has to look at the resulting profile and see, okay, is the overhead maybe too large to be useful? Do I have to use SCORP score? And sometimes, you have to do this multiple times until you reach a configuration that you're happy with and that you can reliably use for the analysis. So we've been working on on automating the cycle, and the basic idea here is to automate the cycle using static analysis, and also looking how we can integrate static analysis with profile information to kind of help the analyst in getting this process done quicker. Our foundation for this is a static code program call graph. And over the years, we've developed a tool called MetaCG, which we use to obtain this call graph. And we have explored 2 major approaches, which we'll talk about here. The first one uses purely static selection. We have a tool called CAPI. And then also you can do some iterative refinement. And there's also a package called Pyra, which Peter will talk about later. And our goals with these tools is first to develop robust approaches on how we can do this in a more researchy setting. And then also we're now trying to make this really viable for large scale codes. So there's not just purely academic, but can be used for let's say CFD applications. So now I want to give a little bit of an introduction to MetaCG, our call graph toolset. So MetaCG is first and foremost a file format for whole program call graphs, where we have nodes and edges, where the nodes are functions, the edges are called relations. And one of the key features of this file format is that nodes and edges can be decorated using arbitrary metadata, and the tools that are included can be extended with plugins, so you can attach this metadata using data generated by the compiler. So here's a very simple example. You have a simple program call graph here, and this is how it looks on the MetaCG format side. So for each function node, you have an entry in this JSON-like format with some information about callers, callees, and then also the metadata. In this case, for example, we can add this num instructions, which just would tell us, okay, how how many instructions do I have in here? So the whole MetaCG project consists of this C++ library to manage and process call graphs and yeah, do file IO. But we also supply a toolchain to generate, merge, and validate this. And this is shown here on the bottom. So as a user, you start with yeah, you see your C++ source files and generate single translation unit call graphs using the CG collector tool, which then can be merged together using CG merge, which then gives you a whole program view. And for validation purposes, if you really want to make sure that this call graph is complete, we also have a utility that kind of compares the static call graph with the output of a SCOP profile, and then you can do some patching if you like. And this can be put into some kind of tool that consumes it. And one of the tools that we have developed to help in this instrumentation selection issue is called CAPI, short for Compiler Assisted Performance Instrumentation. And the idea here is basically to use static analysis to tailor the instrumentation to your measurement objective. So if you already know, for example, you want to focus on I/O, or you're only interested in MPI communication, then you can use this tool to get a tailored configuration for this purpose. Yes, so CAPI provides the ability to compose a pipeline of selector module, and I will show you an example of that. And we have developed this in the context of the Exaform project to do low overhead instrumentation for open foam benchmarks. For example, used for performance analysis and also for performance modeling, for example, using XRP. And the focus with CAPI was really to make this viable for large-scale C++ codes such as OpenFOAM. The main components here is a static selection tool built around a custom query DSL. And then we also provide a runtime library that has interfaces to establish profiling and tracing tools, because we don't have to reinvent the wheel. So we have interfaces to SCOP, XRE, and TALP. And we have this custom runtime because we do a sort of hybrid instrumentation that's adaptable at runtime. And I'll get into that as well. So to give an example, how you could use CAPI, and this is something where we would typically start, for example, for OpenFOAM, in this example, to record call paths that contain MPI communication, and then focus on functions that contain some loops and at least a minimum amount of floating point operation. And in this case, we want to exclude system headers or inline functions. And so very briefly, this is how it would look in a CAPI query. So you can kind of combine and parameter, configure these individual selector modules, and then combine them to get your final configuration. For OpenFOAM, our specific test case, this led to a reduction of 74% of the instrumented functions, which of course doesn't translate to runtime, but also if you kind of reduce the clutter, then the analysis of the resulting profile can be simpler. So now onto the second part, the why we need this special runtime. So what we saw very early is that, well, static selection alone is typically not, well, perfect on the first iteration. So there's always some kind of need for refinement. But if you do static instrumentation and static filtering, this is not really feasible for very large scale applications such as OpenFOAM, because it just takes a long time. You can also do dynamic filtering, but that also retains some overhead. So for that reason, we employ a hybrid instrumentation approach based on LLVM X-ray. And how X-ray works is it kind of inserts what's called NOP slats. So it's a sequence of no-op operations to reserve space for potential measurement points. And then at runtime, these can be patched, meaning they can be replaced with calls to the profiling handler. And we have extended this feature in LLVM with support for instrumenting shared libraries, because it's very important for a lot of scientific codes. So the kind of workflow is shown down here. So you start with your code, which already has these NOP slats in, and at runtime you get the information from the CAPI runtime on what you want to instrument. You do the patching, which then replaces these instructions with the call, well, to a trampoline function, which then passes on the information onto the runtime, and then this can be passed on to SCORP or any other profiling tool. And I have some performance data here. It's probably hard to see. The main takeaway here is that when you have these slats inactive, then there's basically no measurable overhead because they just skipped these knobs, meaning you can use one build configuration both for every profiling purpose. So you can just change the instrumentation on the fly, and you can also use it for production runs. So there's no runtime penalty. Then one final thing. This is something we have recently built on top of CAPI, which is augmentation of MPI traces. And the problem we wanted to tackle here is that using tracing tools, we use this tracing tool X3E by Barcelona. And this tracing tool only records MPI communication by default, just to save space and keep the runtime down. And if you detect some kind of performance issue in this MPI trace, then it can be hard to trace back where this actually is in the code. So you can do stack unwinding, but that's also quite expensive. So what we tried here is to use CAPI to augment these critical trace regions and then instrumenting them to get more information in these specific parts of the code. So what we do is the analyst kind of puts in the surrounding MPI calls and construct a query to CAPI. And using the static call graph, we find possible paths to the call graph that could lead to these critical regions. And then we instrument them. And the result is that we get, in addition to the MPI only trace, which is shown up here, we get detailed information about which function is called. So for example, here we had some load balancing issue, and you could directly see which functions are responsible in code for this. Yes, so now Peter will take over, talking about a bit about the refinement approach.
Yeah, so thanks a lot. So I'm going to talk about PIRA, which is short for Performance Instrumentation Refinement Automation. And the whole idea is just about what Sebastian started with. So the build, run, analyze cycle that is usually kind of used by performance analysts. And the basic idea of PIRA is to combine static and dynamic information kind of in an automated fashion to automate this, this build, run, analyze cycle. So you can just see the workflow that PIRA uses here on the slide. So just as copy, we start with a MetaSG call graph, which is then used as the starting point for this, for the circle, which represents the build, run, analyze cycle. So just as a human performance analyst would do, PIRA builds the application, runs the application, and then uses the information resulting from this copy profile to kind of advance and refine the instrumentation. The same thing is shown here on the right-hand side. So assuming we already are in the cycle, So we first decorate the MetaCG call graph using the metadata that is possible with the profile information, then prune the instrumentation to kind of filter out functions that have no interest because they're just short running or something, and then expand the static use the static information to expand the instrumentation. And then this whole cycle gets repeated basically. So far, Pyra had 3 modes of operation. So it all started with just hotspot detection. So to find hotspots, find parts of the application that could just consume the most runtime. Pyra also supports kernel detection, so filtering out functions based on their scaling behavior, which actually uses extra P. And there's also a load and balance detection mode in Pyra to find those. In a more recent, not yet published work, we extended Pyra with an overhead guided mode. So the innovation here is that we actually, before instrumenting before performing the instrumentation, we estimate the amount of overhead that will be generated, and then we understand instrumentation selection as an optimization problem, basically a binary Knappsack, which kind of maximizes the instrumentation coverage while respecting a shared user-defined overhead budget, which is what you can see here on the right-hand side. Kind of the approach closes in on the overhead budget. All right, to summarize, because we're running out of time, we're building tools for compiler system performance instrumentation. Sebastian presented CAPI, which is a composable selection pipeline based on a domain-specific language and static analysis for instrumentation selection. And Pyra also starts with a much simpler form of static selection and then iteratively refines the instrumentation using profile data. There's a couple of things we're working on right now. The major theme is that we're in the process of improving the usability and the time to profile that our tools kind of offer. We're starting to integrate CAPI and Pyra into a common tool set, and also looking at speeding up the process of Pyra by removing the needs to rebuild the application after every iteration. A colleague of ours is looking into generating the MetaCG call graph already at link time, which makes it easier for the user and also offers a whole program view, which facilitates a few things. We're also taking a look at validating or confirming the call graph at runtime. And as Sebastian talked, we're looking into X-ray to allow for faster instrumentation and also to bring down the amounts of Pyra iterations as a kind of a one-shot approach. And one final thing is that, as I've said, we're in the process of making the tools work for large-scale production codes, and we're also taking a look at Fortran. All right, that's our presentation. We're happy to answer any of your questions.